All right, now that you've all become floating point masters, we're going to talk about how we use floating point inside of our MIPS assembly. You'll notice that the last one or two assembly assignments has to do with floating point. So this should at least help you understand how floating point is handled inside of MIPS. Inside of MIPS, there are a complete separate set of floating point registers. Your regular registers represent integers, and then you have another set of 32 registers that represent floating point. So it's a new set of registers. And then they're paired for double precision. So 0 and 1 is if you're using a double, 2 and 3 is for the next double, etc., etc. Release 2 of MIPS, which we're not going to do, supports more, but whatever, forget it. Floating point instructions only operating on floating point registers. Is anyone confused by that? Oh, good. Okay. Load and store instructions. So there's a C in here. That's how you would load and store from a floating point register. So it's the same thing, except you have that C in there. I don't know what it represent, maybe complex or something, but they decided C. So single precision arithmetic, it's add .s. The S stands for single. So you can add .s into F0 from F1 and F6. Everyone good? Mm-hmm. Now for double, they replace the S with a D.
Whoa.
All right. All right. So you would multiply from what starts at F4 to what starts at F6 back into F4. All right. And then you can do compares if you wish. Don't do compare. Well, yeah, don't.
No, don't.
Yeah. But you can do equivalence, less than or equal. It's just C dot less than or equal dot S. So this is saying control, doing a less than test of a single precision numbers of floating point F3 and F4. So it's saying that if the value stored in F3 is less than F4, then you're storing 1 in the conditional flag. You can also branch on the conditional flag. So after you set the conditional flag, this is important. Notice that this is saying if F3, the value in F3 is less than the value in F4, turn the conditional flag on, aka set it to 1. Otherwise, you set it to 0. So you branch on the conditional flag, or on the integer flag, or the floating point flag to some target. Here we go. Here's a coding example of how we might convert from Fahrenheit to Celsius, which the rest of the world uses, but we don't care because we're America. Right.
Who's been to the moon and who hasn't?
Yeah. Yeah. My favorite of that one was, who has a flying space car? Us.
Yeah.
Who's the only country that eats Tide detergent? Us.
We're evolving fast.
They have chocolate now.
Oh yeah, there's chocolate candy that's shaped as Tide Pods.
There's marketing shaped. I think it's Twix, Mars, and Mounds have chocolate that are called pods, and they're shaped like
so
Tide
weak.
Pods.
Just eat the Tide Pods.
Did y'all have
It's
to
a
do that
real
growing
thing.
up?
It's on Amazon.
The Tide Challenge?
Straight up eat the Tide Pods.
No. Okay, good.
Because we don't want to die or be
I say
hospitalized.
natural selection.
Yeah, honestly, we should
Natural
put warning
selection.
labels.
I'm willing to hear.
All right. All right. Well, anyways, continuing on.
Too many people. Natural selection.
Here for a good time, not a long time.
So, all right. Back in here. Floating. Yeah, this is going to be terrible. F to C. We're going to load at F16 from, all right, the global pointer, some constant, aka 5.0. The other constant, 9.0, into these two floating point registers. Thank you, Kai. See, he's just cheering me on. We'll go ahead and do the division. 5 divided by 9, store that back into F16. Everyone following me so far?
Is that a global pointer and offset?
The global pointer,
Or that's where the program starts, or?
yeah, that's where the program starts. Usually you store your literals, 5.0, 9.0, and 32.0, back up in data, and they use your global pointer to point to there, and then you have some offset in here that programmed by the assembly, and it goes ahead and puts that in there for you. Great question. Any others? Nope. Okay. Now we're going to load in the 32, put it into F18. We're going to subtract, what was it called? F18 from F12. Where did F12 come from? So F12 is probably the fahar. Yeah. So you subtract it.
It's supposed to be the beginning of Fahrenheit.
Yeah, whatever.
Oh, it is. Hey.
Yeah, it's Fahrenheit. It is.
Yay.
And then we'll multiply what we got from here times the answer over here. Store that into F0. Wow.
Well, I was going to say far is in F12.
Yeah. So far as an F. Oh, it says that right up here.
Right there.
And the result's going to be an F0. Literals are in global memory space. Hey, look, reading the slide. Nice. Nice. Well played. And then you return. All right, everyone see how that happened?
Yes.
Any questions?
Nope.
Okay. How about array multiplication? Do you think that happens a lot?
Yes.
Yes. It happens all the time.
It doesn't exist.
All right. So you have x and y and z, and you want to basically multiply y times z and put it into x. So if you all remember from your matrix how many of y'all have done linear algebra?
Doing it right now.
Currently in it. Yeah.
Have you done matrix multiplication?
I think so.
Yeah.
Yeah. So you have your two matrices, and you go row, column, you
Yeah.
multiply and add them. Okay.
Oh yeah.
Yeah.
So,
It's only calculus 3 too.
Which we found out a way to do pretty much everything in that class with our calculator.
Yes.
Oh my God.
So everything that she teaches us, I'm like, yeah, that's I can do that here.
yeah, computer scientists usually have a very easy time in that course.
Yeah. Because she's like teaching us this whole elaborate way to
Well,
do it.
it's
I'm
funny
like, "Here it
because
is."
the math major's like, all right, guys, this is a matrix. Whoa, 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 hold on.
Yeah.
And by the time we're there, like, yes, we got it.
Yeah.
It's only a 2D matrix. Oh wow, well, this is even easier.
That's it.
That's it? Yeah,
We're just
exactly.
like,
That's it.
plug it into the computer.
She's like, we're not going to deal with 3D matrices. Alright.
All right. So
The fun
IJK.
ones?
Hopefully this formula makes some sense. How we're doing matrix multiplication. We'll say addresses of x, y, z are in argument 0, argument 1, argument 2, and IJK are in stored, the saved 0, 1, and 2. All right, great. So how does this look in assembly?
Oh god.
This looks terrible, but it's not. It's not.
Gross.
Yeah, right. It's not gross. Thank you. All right. Why are we loading 32 into T1? Because that's what all our for loops go up to. I is going to start at 0, J is going to start at 0, and K starts at 0. See how they put the code over here to help you?
Uh-oh.
It is
Oh,
nice. It is nice. All right, so what's SLL?
Simulate
Nice. Well played.
Is it really?
this. Yeah.
In this.
Is it not simulate?
So we're doing I times 32. Notice that, wait, hold on a second. What's going on here? We have S0, which is 0, I, multiplying it by 32, and then you're going to load that into T2. Right, isn't that this thing? I mean, this
You're
guy.
asking the wrong people.
Yeah, the size of row X. Mm-hmm. And then you're going to add what's coming in J. So now you're going to, whoa, I went
Whoa.
to
Don't break it.
right down here. And then you, wait a minute, what is going on? Hold on.
That's not a good sign.
No, it's not. I times 32. Oh, I see what's going on here. Okay. No. How do we calculate that? Where is that? The x sub I sub j for the people at home.
Somewhere.
Are we talking about in the array?
Where is that
in the
memory?
matrix.
How do we get to that? Because we have x, and x is a pointer, right?
Yes.
Yes. So it's pointing to some memory spot somewhere. It might be the stack or the heap. But what is x actually pointing to?
It's pointing to, well, in this case, in the 2D array, it's pointing to a pointer that points to
All right, so these are actually Yes.
Yeah.
It's
Correct, and this is where C is kind of weird. This is actually a single pointer, but it's treated as a double pointer, so when you reference it, it knows how to jump down. So I guess I probably didn't go into this in C, so let me explain this. Each row, how many elements are in each row? Well, we're saying it's a 32 by 32 matrix, correct? So I'm sorry, and in computer memory, when you store it this way, it's just one long array. So the first 32 slots are for row 0, the second 32 slots are for row 1, the next 32 are for row 2, etc., etc., etc. Okay?
that looks bad.
What?
That would look bad.
And
So
then
the
slot,
in order to
very long.
slot 32 would technically then be beginning of the columns. Did you do 0 to 31?
0 to 31. So 32 is actually going to be the first element of the next row.
Yeah.
Right.
Yeah.
Yes.
We're doing row major order. All right. So in order to figure out I is going to tell you how many 32s you're going to jump down.
Gotcha.
Right?
Yeah.
So over here, I times 32 into T2, so you can start finding the address. And we're going to then add J to it, which is S1, right? We said S1 is J. Please tell yes. Yes, we are.
Why would they just name it Alpha?
And then the byte offset of J. So the trick here is that, now you got to remember, so 32, this is confusing to read at first. It's 32 somethings, but it's a 64-bit double precision. So it's 32 times 8, because this is 8 bytes. So what's the size of each row? It's 8 times 32, which is what? Too much? Okay. 2 to the 5th times 2 to the 3rd, which is 2 to the 8th.
Like that just made it any easier.
It didn't?
I don't like doing these.
All right.
Not
So
my
each row is
256.
256 bytes.
It takes
If you notice over here,
oh.
there's that 2 to the 5th, 2 to the 3rd. That's how you know how many byte offset of J. Then you can finally get the byte address of X sub I sub J. And then you can load in the 8 bytes of X sub I sub J. Kind of following how this happened?
It's making me want to go back to C.
Yeah, isn't C nice? It is, isn't it?
I'm not writing in assembly.
I never thought I'd say that.
Never what?
So I never thought I'd say that.
C is very nice. It does a lot of work for you. All right, we're going to do the same thing again because we have to get it for Y and Z, but this time they're going to store Z sub K sub J to F16, so F4. Let me go ahead and write this to the side. $sign F4 is equal to X sub I. I'm going to erase this. Sub J. And then we have what? $sign F16 is equal to Z sub K sub J. All right. Everyone following me so far? John is shaking his head.
I'll follow you. I'll eventually get there.
You eventually get there, unless we just skip ahead. Now we're going to do the same thing with Y. So it'll be $sign F18. Y sub I sub K. So we do the calculations, we load it.
So all those operations, like all those blocks, are like 5 operations, like that we just passed.
This is
all
shift.
those
I just
does-
realized I never told you that. Shift.
Gotcha.
Yeah.
Yeah.
You were like
Oh,
singly
right.
leave this, you're like, good
That's-
guess, and then you just kept going.
But that's all that does is we're just fighting.
If you shift it to the
those-
left by 5, you're
values.
multiplying it by 2 to the 5th, aka 32.
Okay.
So that was that number. And then
Okay.
you know,
Okay, not singly.
that makes much more sense.
I'm sorry,
Right.
guys.
I remember
It's okay.
So all
That
of
was
it's just
classic.
But that does make more sense.
Okay, so you shift I, which is essentially multiplying by 32. Shifting is always faster than multiplication. It's a single cycle operation, always, because you just do a barrel shifter. Don't worry about digital logics. Anyways, multiply by 32, and then the actual adding, and then you, again, shift it by 3, and then add the file number to get the final byte address, and then you can finally load those 4 bytes. Now, you can do the multiplication.
I can finally do stuff.
F16 will be y sub I sub k times z sub k sub j, which is this guy down here. And then you want to go ahead and add that back into F4, which was storing x. F4 was storing x, so you just do F4 plus what we just multiplied here. Put that back into F4. And now, let's see what they're doing here. S2, adding k. If it's not 32, go to L3, because that means we have to exit. Otherwise, you go ahead and you write that answer back out into the X matrix, because you need to store it, right? Because this is storing. So they calculate this answer, and then they store it back out.
Into
X.
right. So basically, you're overwriting.
Yes. Yeah, you're overriding it. But you're pulling an X, so you're actually appending to it. Because remember the calculation, you pulled X here, you pulled Z here, you pulled Y here, you do the calculations, which was multiplying the Y and Z, and then you add it to your X variable, so then you add it back in. You add J, you add I, that should be it. Good. And then you just keep branching in case you need to do anything. Until the loop is done, incrementing I and J. All right, how was that? Which one's better, this code or that code?
That code.
Good.
Stick with C.
Stick with C. Good.
Do we have
So
to do
that all of that is just one like.
Tiny little thing.
It's just these 3 for loops.
Yeah, but is all that code that's on like the other page? Is that just one run for the loop?
No, that sets up the loops.
Oh, okay.
Because remember, you start up here, and then you have
Oh,
your
and then-
branches down here
Okay.
after you add them.
Are we coding that?
But like,
No.
No.
Oh,
Okay.
thank God. I'm sitting there like,
I
oh.
want to do that.
Huh?
the majority of that looks like it's just taken up by just finding the values in the arrays there. Really.
You mean doing this whole calculation over here?
Yeah.
Yes.
That's
That's
fantastic.
yeah. That's a lot of work.
Yeah.
That's too much work.
How you doing, Sydney?
Although that's a neat trick with the shifting. It's a good thing. So
Yeah, it is
That
good.
just reminds me of
Doing well, Melina?
data structures.
The stand doesn't do the structures.
All right.
Should we structures?
All right. Let's go ahead and take pause for a moment.